violations, CTCs, closed time-like curves. Then we will talk about 3 or 4 deformations. The charge generalization of the Johnson-Saltis and the acceleration, the Johnson-Saltis with acceleration, and then CPR black hole with charge and with acceleration. So these deformations we will, so everybody knows these Einstein's field equations. I don't think I have to tell you. And these are the first solutions, the Schwarzschild solution with one parameter, the mass only, and Reisner and Armstrong space-time with 2 parameters, mass and charge. So this is the Kerr space-time with 3 parameters, 2 parameters, mass and angular momentum. And if we put angular momentum A equal to 0, of course we get the Schwarzschild solution. So this is in Boyle-Linguist coordinates, the most common form for the Kerr space-time. This is the Kerr-Newman, that is the charged Kerr. So this is, here you can see there is a Q also over there. So if we put both Q and angular momentum equal to 0, we recover the original Schwarzschild solution. Okay, so in this solution, for example, if we want to study the surfaces where T is constant and R is constant. So in any of the previous space-times, if we want to study the surfaces T constant and R constant surfaces, what we get are spheres and spheroids. So in 4, for example, in this equation 4, we have, this is the surface we get when we put T equal to constant and R equal to constant. And in the Kerr space-time, if we take the limit m going to infinity, we get this equation, which actually represents the Minkowski space-time in spheroidal coordinates. So if we plot these spheres and spheroids, okay. In Cartesian coordinates, this equation can be written in the form 6, where these are the transformations which convert the original equation into this Minkowski space-time. Or for this the spatial part actually can be written in this form as well, which is in the polar coordinates. Now this actually represents 3 surfaces. It's a prolet spheroid if A square is taken as positive, and oblate spheroid if A square is negative, and a sphere or normal sphere where A square equal to 0. So in some sense, these are the deformations of a sphere in the Minkowski space. Okay, so this is the diagram where this yellow is the prolet spheroid, this green is the sphere, and red is the oblate sphere. So deformations in Minkowski space. Okay, so why we need to deform the Francesco was talking about some historical tests, particularly these. He explained in detail this test in 1919, and the other tests that were done much later. And the tests in solar system, they started in 60s, and then so these are all weak gravitational field regime tests. Different tests taken over the last different many years. In strong regime, of course, we need to do the astrophysical test in the black hole space-time if we want to do the test in the strong regime. Okay, so Babu Murad also showed this slide. The no air theorem. I said you also showed this slide. Yeah, but I noted that there was this the capital letters were written correctly. So here although I asked my students to put these things correctly, but in my slide you see there's some editorial mistakes. They should all be capital letters. But anyhow, I think this is taken from Google. So no-hair theorem simply means that the black hole can only have three parameters: the mass, charge, and angular momentum, M, A, and Q. Okay, so what is the Kerr black hole hypothesis? This Kerr black hole hypothesis says that the Kerr black hole is a solution of Einstein field equation which is stationary, asymptotically flat, axisymmetric, vacuum solution. It's regular outside the event horizon and there's no CTCs, no closed time-like curves. Okay, so as Babu Murad also presented in his nice talk, that the astrophysical black holes are actually very close to the Kerr solution. So they represent the Kerr black hole physically, actually. So most of the black holes that we see, they are described by Kerr matrix, but perhaps some properties we need to study because of these deformations that we will introduce. Okay. So this is basically the Kerr black hole hypothesis, that the electromagnetic spectrum is measured in the Kerr space-time as a result, and this compared with the observational data to see if it is actually represented by the Kerr, or we need to have some deformations in the space-time. And in the same, actually using this approach, this non-Kerr space-time was introduced that we call as Johansen-Saltis earlier. And in this way, we can check the non-Kerr behavior of these space-times. And these deviations are introduced in the Kerr solution, and there are many ways to introduce these deviations. We will see a couple of them. How can we introduce these deformations in the Kerr? People have done these in different ways. So there are two approaches basically. One is called the top-bottom approach. That is, we modify and parameterize the Kerr solution by constraining the deviations from observations. So we see from the observational data what deformations we need to introduce. And the other is the bottom-top approach. That is, we introduce some deviation parameters in this, and then we try to find the values of those parameters by considering the observational data. Okay, so this talk will mainly be about these 4 or 5 deformations. The first one, which is very popular, was done by Johnson and Saltis in 2011, and it's most commonly known as the non-Kerr solution. And these are the deformations introduced in our group by my students Rehanna and Usman. So we will be introducing charge and then acceleration in this, and then the CPR black hole, and then we will introduce acceleration in it. This paper is also submitted somewhere, and we are in the process of responding to the questions raised by the reviewer. Okay, so there are different methods to construct this. One is if we take this Schwarzschild metric, for example, where this function is known, and in the TR sector, if this TR sector, we multiplied FR by this 1 plus HR, where HR is this series in the ratio of M over R. So this, we expand this in the ratio of mass over radius. And the deformed solution, if we substitute this, multiply this FR with 1 plus HR, we get the solution again. Then we introduce these transformations. So this is F into 1 plus HR, and this, after this coordinate transformation, we get this. And if we convert this into tetrad formalism, this will be this Newman-Penrose formalism. Inverse matrix is given by this, where the null vectors are given. These are the 4 null vectors. First 2 are real, and then this is the M mu is complex, and this is the complex conjugate. And this is called the complexification of variables, where 1 over R is actually replaced by this R, and where R bar is its complex conjugate. And 1 over R square is, of course, then written by this. So introducing these, using these substitutions, and the original null vector, they will be converted into these four. You see now the H factor is introduced. This is the deformation factor, which measures the deformation from the usual Kerr black hole. Again, this mu is used.
Khalid, almost the time.
Okay, so mu is the complex, and this. So if you use these deformations and using this coordinate transformation, finally we get this form, or in the line element form, this can be written in Boyle linguist coordinates. Oh, this is the matrix of the non-Kerr black hole. Okay, this does not have charge or any other parameter, just the mass. But this is the usual non-Kerr Johnson-Saltus space-time. Now if we introduce, I skip this slide, and we draw the Killing horizons and see how they differ from the usual Kerr. And I want to go to the charge generalization. So here if we introduce this 4-vector potential, the Q over R, and this parameter as defined earlier, the non-Kerr space-time, now this is charge non-Kerr space-time. Again, as one should expect, if we put charge equal to 0, this should reduce to the usual Johnson-Saltus space-time. Okay, and now we can introduce another parameter, that is the acceleration here. So this is the non-Kerr with acceleration. I think I skipped the procedure and show you the line element only. Okay. So here this alpha parameter represents the acceleration. A is the angular momentum. If we put both of them 0, of course we will get the original space-time. Okay, so this was an interesting black hole introduced by Cardozo, Pani, and Rico, usually known as the CPR black hole. So here, this is also a deformation of the Kerr black hole. The difference between the earlier and this is there is a large number of parameters introduced. For example, here E, if we put this epsilon to T and epsilon to E, if we put both of them equal, we get the original Johnson-Saltus. So in some sense, this is the generalization of the original non-Kerr. So generalization of the Johnson-Saltus. So I think I should only, so this is the space-time
Khalid,
yes.
I think it's the time because you don't have time.
Okay, so this is the final, this contains everything. The non-Kerr parameter, the acceleration, charge, angular momentum, and everything. So I think this is conclusion states almost everything that I've already said. Okay, thank you very much.
Let us thank Saifullah for very interesting presentation. Are there questions to Khalid? Because this topic is very interesting. Because deformed black hole is, if the solution satisfies to the pure equations, it is very nice work. Are there questions?
Yes. 2 questions.
Yes, there are some questions. Yes.
1 comment.
Okay, ask, please.
The question first is the acceleration you were talking about is in the polar direction only?
No, it's in the axial direction.
It was with theta, I thought.
So it's the acceleration is not in the angular, not the rotation, but it's acceleration in one.
So it's azimuthal.
Yes.
Okay, thanks. The second was just a comment. You said 2 parameters for the curve. There are 3. Yes. 2 for the killing vectors, the third for the killing tensor.
Yeah.
The total length.
Okay. So when I was saying parameter, I was considering mass, charge, and angular momentum. So in that term, I was taking.
But the angular momentum squared.
Yes, that is also. Yeah. Okay.
So if there are no questions, then let us thank speaker. and what we will do next. Organizers, what is the next? Zeeshan, please announce.
Next is tea break.
How many minutes?
So 10 minutes break, 10 minutes break.
Okay.
Okay,
See
thank
you
you.
in 10 minutes.
Yes, thank you.